I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
or
space, time,
the brain,
life, the universe.
Hello, this week the crickets that are showing scientists how to make improved hearing aids, better wind turbines thanks to dragonflies, and the aircraft that repairs itself. This week we're looking at bio-inspired technology.
Plus, in the news, why heart disease begins much earlier than we thought, whether science publishing is facing a crisis, and the future of satellite navigation. I'm Izzy Clark.
I'm Chris Smith, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
Now, first this week, about one person in every 100 suffers from the brain condition epilepsy, which can lead to fits and seizures. It's very disruptive for an individual's life, and up to a third of people with it can't adequately control their condition with drugs. Now, a team from Cambridge University have designed a brain implant that can release tiny doses of anti-epilepsy medication precisely where and only when they're needed. Chris Proctor designed the system. Chris, when someone's having an epileptic seizure, what's actually going on in their brain?
So an epileptic seizure is characterized by bursts of activity in the brain. So usually some collection of cells, they're sending messages to all the cells around them, and then this message gets propagated through the other cells throughout the brain. And this can lead to pretty significant symptoms such as loss of consciousness, memory loss, and even tingling sensations in the limbs or convulsions.
Now, we've said that maybe 1 in 3 people can't control this condition with drugs. Obviously, 2/3 of people can, but for those people who can't, that's where your device might come in handy.
Right, exactly. So typically for the 1 in 3 patients roughly that do not respond to traditional medicines, the next best option is to go in the brain and cut out the area of the brain that's causing the problem. Some cases this isn't possible and it's never really desirable. So what we've developed is a solution where you could implant a very tiny device that could detect when a seizure is coming and then intervene to stop that seizure.
What does it look like?
So the implant is quite small. It's roughly the size of 2 human hairs put together. At the very tip of it, there's an outlet for drugs to come out, as well as 2 tiny sensors to monitor the local activity in the brain.
So it's eavesdropping on the neurological activity.
Exactly.
And what it can tell when there's the sort of signature departure from normal that signals or heralds a seizure is on the way.
Exactly.
And how does that then know to dispense agents that will control the seizure?
So with the implant we've developed so far, we want to work towards a closed-loop system, so the device would have some electronics where it would be monitoring in real time what's happening and then know when to intervene. We haven't incorporated that yet. Long-term, that's where we're going. But for the time being, we are actually monitoring the activity ourselves. Then we could see the seizure was coming, and then we could intervene at that point.
And how would it expel the drugs from the implant onto the bit of the brain that needs them?
So the way that this technology works, it's called a ion pump, an electrophoretic delivery device. So we create a small electric field, and then this electric field actually pushes the drug molecules out of the device through some membrane and then into the brain. And what's really significant about this is because it's operating in response to an electric field, that gives us good control of when drugs are delivered and when they're not, how much drug is coming out. And also equally important, only the drug molecules are coming out. So this does not really impact the local pressure in the environment. So the cells right outside of the device are not physically displaced by the drugs coming out. And this is rather important for maintaining long-term effectiveness of the technology.
If you're using an electric field to push the drugs out, does that mean that only certain types of drug molecules that respond to an electric field could be used by the device?
Yes, so the drug molecules have to have some sort of ionic form. It means they have to carry some charge. But it turns out a lot of drugs actually do carry some charge, including inhibitory neurotransmitters that we use in this study, which are native to the body.
So could you take, say, a cocktail of agents, because we know that everyone is different, so everyone's presentation, disease or response to drugs might be different. Could you mix up a cocktail unique to a person and squeeze that out of the implant in order to achieve optimum control of an individual's problem?
You absolutely could. So long as they're all charged molecules. I mean, this is something we're pursuing now, kind of working towards optimizing the dose of one or multiple drugs to better affect a seizure or some other disorder.
How do you actually get the implant in the first place, and how do you know where to put it?
So in the study we did so far, we were actually having another implant in place to inject some chemicals to cause a seizure. So we created ourselves a seizure. So we knew where to put our device. We wanted to be at where the seizure is located. But in practice today, it's actually quite standard to map brain activity using a series of electrodes either on the surface of the brain or going into the brain. And from that, you can determine where the seizure is emanating from. So that would be where you would put the device.
And if it's only the size of a couple of human hairs laid side by side, that's incredibly small. Can it hold much drug? Is that enough?
So what we found in this study, actually, surprisingly, a very small amount of drug goes a long way. So less than 1% of the loaded capacity of the drug was able to completely prevent what would have been otherwise very catastrophic seizure-like activity in animals.
And lastly, the brain isn't the only electrically active organ in the body. There are things like the heart as well, where drugs squirted onto specific areas might make a very big difference to a person. Could you deploy this somewhere else as well?
Yeah, there's tremendous potential to use this type of platform to deliver drugs all throughout the body, the heart, the peripheral nervous system, and I think there's a lot of exciting applications, and we're really looking forward to applying this more widely.
We have an investor potentially sitting next to you. That's Peter Cowley. He'll be on later in the programme. You might better tap him up for a few bob. Thank you very much. That's Chris Proctor. The study you were just describing, Chris, was out this week in the journal Science Advances.
Sounds like very promising work. Now, smoking and drinking damage our heart and blood vessels, but when does the damage begin to set in? New research following teenagers suggests that as early as age 17, there may already be signs of disease developing. Adam Murphy spoke to the study's author from UCL, John Deanfield.
My interest is in understanding how arterial disease develops in all of us that eventually, in many of us, unfortunately, leads to heart attacks and strokes in later life. Despite the fact that these clinical problems occur usually in our 50s and 60s, what we've learned is the underlying arterial disease starts decades earlier, and it often starts in teenagers and young adults.
And what happens in these young people? How do we know that the disease is starting?
So we use an ultrasound-based technique where we image the artery and we look at the response to blood flow in the artery and how the artery moves when the blood is going down in response to the heartbeat. And there is this formula we can apply to see how adaptable the arteries are to changes in blood flow and pressure. And that represents a stiffness index. And when you damage your arteries, the first thing you do is to damage the lining of the arteries. And the second thing that happens is the artery, as a consequence, becomes much more stiff and rigid. And that's a beginning of a process that eventually leads to clinical problems in later life.
How did you find this in these young people?
So what we did was to study a group of young people who are part of a very big longitudinal study. It started in Bristol when they were born. It's called the ALSPAC study. And what we did was to take the children who we've been following up and look at their arteries and look at the function of their arteries in relationship to two very important potential factors that might relate to heart disease, and that is smoking and alcohol consumption. Now, we looked at smoking by looking at how many cigarettes they had been exposed to in their life. And alcohol we looked at in a little bit more detail, looking at the pattern of drinking in terms of not only how often they were drinking, but also to see what happened when they drank in a sort of intensive way, in a binge drinking way on one day, for example, which is the common pattern often in young people. And we were able to show that the smoking, even at very low levels, was associated with signs of arterial damage. Alcohol consumption was associated with signs of arterial damage, but it was particularly the binge drinking that was bad for the arteries. But when the young people both smoked and drank alcohol in that way, the arterial damage was added on. It was cumulative. So it was much worse to drink and smoke than it was to smoke only and drink only. But all of those factors were already showing signs of damage to the arteries in teenage years, which is very early on.
What is the impact for their later life, and is there any chance of recovery from this?
So that's a really good question. We now know from lots of studies that the disease that eventually causes so many problems in later life starts early, and that it is progressive with time, and it is the exposure to risk factors over time that drives the development of arterial disease. Now, if you were to take an elderly person who's already got established arterial disease and try to reverse the problem, you'd be disappointed because those accumulated diseases are largely irreversible, and we have to deal with them with complex and expensive interventions like stents or operations to bypass them. But at a young age, potentially, the disease is reversible. And that's what we got a clue for in this study as well, because if we looked at the arteries of the young people who'd stopped smoking, their arterial function was the same as the young people who had never smoked. Potentially, these early damages are reversible by stopping smoking early. And I think that's a very positive message from this study.
Do we know when it stops being reversible, when the arteries can't bounce back anymore?
There probably isn't a magic time. A young person who smokes continuously from their 30s loses on average about a decade of life expectancy. That's a huge amount of life lost. But if you stop at 30, the good news is you regain about 90% of that. If you stop when in your 50s and 60s, you regain around 40% only. So there's everything to gain by stopping early.
If you could have people take one thing away from this study, what would you want them to take from it?
Never smoke cigarettes. The effect of cigarette smoking is much greater on arterial health in the future than alcohol consumption. Smoking is always bad. It really is a crazy thing to do for a young person who wants to have a healthy future.
Wise words there from John Deanfield speaking to Adam Murphy, and that research has just been published in the European Heart Journal.
From baffling British weather,
sideways spines of the vertebrae coming off here,
to looking at a cheetah from the inside out, games making their way to the clinic, and what to eat in your garden. The Naked Scientists In Short podcasts bring you a top-up of short, compelling science stories. Listen and download for free at nakedscientist.com/short or subscribe to Naked Specials wherever you get your podcasts.
You're listening to The Naked Scientists with me, Chris Smith, and also with Izzy Clark. Still to come, why the UK's got to get its own satellite navigation system, and we'll be exploring the latest technology inspired by nature. Before that, though, it's time for this week's myth conception, and Tamsin Bell is laying a rainy myth to rest.
You may have heard the expression that if you see cows lying down, it is most likely going to rain. In fact, 61% of us Brits believe this handy method is an accurate way to predict the weather. It's not entirely clear where this saying originated, but it is used widely in the British countryside. So, is there any good reason to believe that cows can predict the weather? It would certainly be impressive if cows had this unusual intuition. Unfortunately, however, there doesn't seem to be much evidence to support this. When researchers observe cow behaviour, they tend to categorise this into 3 patterns: lying, standing, or grazing. Overall, cows seem to be sedentary beasts. They spend up to 50% of their time lying down, more or less regardless of environmental conditions, and they show significant signs of stress if they are prevented from doing so, even for a short time. This means that at any particular time, your odds of seeing a cow lying down are pretty high. Although, given the British climate, farmers can be forgiven for assuming this behaviour to be a good predictor of rain. Even if they don't have the ability to predict the rain, the weather does seem to affect cows' behaviour. For example, they seem to have a strong aversion to lying down in the mud, so much so that in experimental conditions they prefer concrete over muddy ground. This seems to result in cows being much more likely to lie down whilst it's raining, presumably in order to protect their patch of dry land, or maybe just to keep their udders warm. However, if they are caught standing in the rain, they are much more likely to seek out shelter than lie down. Additionally, a small amount of light rain might actually encourage cows to get up and graze before the grass gets too wet. It seems that cows graze less when there is a large amount of moisture in the grass, although it is not entirely clear why this might be. So, it looks like cows aren't much use as barometers. But are there any other creatures out there that might be able to predict the weather? The answer is a solid maybe. For example, birds and bees seem to be able to sense changes in barometric pressure occurring before thunderstorms. This prompts them to find shelter. So if the sky is looking ominously empty, that might mean there's a storm brewing. Studies into animal behaviour also indicate that birds change their song before it rains, although this effect might be a little bit subtle for the average nature lover to detect. Should we want to look at something closer in scale to cows, there's some evidence that elephants might be able to detect rainstorms due to their amazing low-frequency hearing. They can hear a storm coming from up to 150 miles away. Although, unlike most of us, they seem to want to head towards the rain rather than avoid it. On balance, it looks like we might just be better off relying on the weather forecast than our good friend Daisy.
Very amusing. And if you think you've had some suspicious sounding science, then email chris@thenakedscientist.com and we'll take a look.
I get the impression she was milking that myth a bit. Do you agree?
Oh, very good, very good.
Now, more than 1.5 million papers describing new scientific breakthroughs get published every single year. But is this science actually trustworthy? The answer is that if it is, then it ought to be possible to reproduce the results independently, shouldn't it?
But when researchers from the Virginia-based Centre for Open Science set out to do this, even with papers published in so-called high-impact journals, they weren't always getting the same results. I spoke to Malcolm MacLeod from the University of Edinburgh, who reviewed their work.
Essentially what they were trying to do was to say, let's take some findings from social sciences research which have been published in journals of high impact like Nature and Science, and see whether those findings hold out when we try and test them again in exactly the same way as the original circumstances of testing. And they did that for 21, and they found that for 13 they probably could, and for the rest not so well. Now, there are 3 patterns that they found, essentially. For some studies, they were able to replicate both the direction of the effect that had been reported and also the size of that effect. For others, they showed the same direction effect, but the effect size was a lot smaller. And for others, there was no effect at all in the replication studies. And that pattern fits with what we've seen now, that some studies replicate and others don't replicate at all.
So when we say this direction, are we saying that we've done what they've said they've done in the paper, but actually we're only getting something that looks a bit like that result, and actually it's not as effective as they've reported?
That's exactly right. So on average, the effect sizes in the replication studies are about half the size as they were in the originator studies. And that's potentially important if you're thinking about taking, for instance, a drug that was developed for stroke and tested through the laboratory, through cell culture and animal models, and you look at all of those data and you say, crikey, this drug looks highly effective. It improves outcome by 40 or 50%, and so if we're doing a human clinical trial, we should certainly do one, and we won't need very many humans in that trial to show that it works. But if the true effect size is substantially smaller, then you've designed your clinical trial wrong, and actually the whole reason for going into clinical trial might be incomplete. These studies were sampled from those published in high-impact journals, and previously one of the comments around about the replication efforts had been, well, of course, if you look at everything across the range of all journals, then you're going to get some things which work and some things that don't. But if you looked at things published in journals of high impact, then you wouldn't have that problem. And it turns out that, in fact, you do have that problem. I think there's a wider context here, because often these efforts at replication are seen to be a criticism of a particular community of researchers in a particular field. But the fact is that in whichever fields we have looked for evidence of difficulties with replication, we've found them. And the more that goes on, and with the contribution of this recent study, the more it becomes highly likely that these problems would be prevalent in any field of research which you chose to study.
Because that's what I was going to ask. I mean, are other sciences at risk, and how can you reduce that?
Other sciences are at risk. We need to do more to improve the reporting, the design and the conduct of those studies. The second thing that we can do is we can try and understand why replication might not occur, because now in these replication studies, they've done everything they can to nail it down so they're doing exactly the same thing. Every variable which they consider to be important to the outcome is controlled and is the same in the 2 studies. So what that implies is that there is some variable which we don't know is important, which is driving differences in the observed outcome, that if we understood it, it might tell us a bit more about the phenomena being tested.
I see. How can we trust what is published?
So if you think about research as a product, then you need the user of the research to be able to do due diligence on whether that research does what it says on the tin. And that involves skills in critical appraisal, which we are now teaching more in our universities and in our institutions. And it also means as if a journal can really go down the line of doing critical appraisal on the work which they publish, then it will increase the quality and the veracity and the trustability of their outputs. And journals are doing this now, and time will tell whether that has an effect. But the bottom line is, in the same way that you wouldn't buy a car without taking it for a test drive, you shouldn't take a research finding from a paper and believe it to be true. Just because it's newsworthy doesn't mean it's true.
Malcolm MacLeod from the University of Edinburgh. His review and the original study from the Centre for Open Science were published recently in Nature Human Behaviour.
Now, it's anticipated that funding for the UK to set up its own satellite navigation system is going to be announced soon, and this is going to be a rival for the European Union's Galileo project that the UK looks like it's going to be excluded from after Brexit. But how does GPS work, and could technology actually improve it? Well, with us to talk about this is our tech correspondent, that's Peter Cowley. Peter, why do we actually need our own GPS system in the first place? Because even if we fall out big time with the EU, assuming we haven't already, we can use the American one, can't we?
Yes, hello, Chris. Yes and no. It all comes down to how much we trust each other. In all of these satellite systems, there are two times when things can be either reduced in accuracy or switched off. So the switching off would generally be used, as was used in the Gulf War, just by the system having some sort of encryption putting in place, and then nobody can use it at all. Now, you can imagine how many people use it, particularly millennials who don't know how to walk right down in the centre of London or the centre of Cambridge and just got completely lost without GPS. We'd be completely stuck there. So that's why the Russians set up their own system. That's why the Chinese set up their own systems. That's why Galileo was set up, so that we're independent of each other should something horrible go wrong.
Not just navigation, though, is it? We use the time signatures for even, I learned the other day, ATM machines at banks, knowing when they're doing transactions. The time signatures arrive by GPS.
I'm not surprised at all, because it's a constellation of atomic clocks floating around, and several of them. So there's 30 or so in each system, and each of them is incredibly accurate.
And the anticipated price, if we have to go down this route, will be what, to set our own system up?
The European system was set up in about 2005. It started, and the first satellites launched in 2011, and they're just about ready now. There's quite a few satellites up there. The total cost, of course, was an overrun. It was about 10 billion euros, of which the UK has paid 1.2 billion euros already and may want that back, and that's part of the big negotiating mix that's going on with Brexit. It's a complex project to put them out there. It's a number of satellites transmitting a signal down throughout the whole globe.
Do you not think it's fairly daring on the part of the EU to chuck us out? Because the UK has been pretty instrumental in doing a lot of the coding and the security that's associated with the Galileo system. This would be a bit like Microsoft sort of chucking out half the coders who wrote Windows and saying, thank you very much, we'll do fine, no thank you.
That's correct, that some of the encryption was done in the UK. And also the UK is pretty well known for quite good satellites. There's a cluster of skills in Surrey and one up in Glasgow. So yes, that would have to be rewritten. So they would cost money. But at the same time, there are a whole stack of things that Brexit is discussing. That might be one of them.
Now, you say that there's an opportunity for us to go one better and improve on the system. In what way?
So think about it. You've got a satellite that's floating around about 11 or 12,000 miles up there, 500 watts being sent out. It works out we're getting the most amazingly small amount of power down on the Earth, on the antenna. About one followed
in your detector, you mean, the thing that's picking it up?
Yes, exactly, which is a very small antenna only. One with about 17 or 18 noughts afterwards. And I did a rough calculation, which I might be miles out, but I think if you were to shine it down and try to boil a kettle, with that power, it would take the lifetime of the universe to actually boil that kettle. I may be out by lots of zeros.
So what you're saying is that the satellites are sending a minuscule amount of energy, which we're detecting with our devices. So what's the problem with that?
The problem is it doesn't get inside buildings very easily. And more importantly, as it's going down in a city where there are skyscrapers there, or even smaller buildings, it's bouncing off them. And it works on the basis of time of flight from the satellite to the receiver. So if it's bouncing around, obviously the time of flight will be longer, and therefore it becomes less accurate.
These are urban canyons, these effects.
Yes, these canyon city, as they call it. And also indoors as well.
So how can we get around that then?
Well, there's a company which I'm invested in here in Cambridge called Focal Point Positioning, and I'm sure there's plenty of other companies around the world, which is doing it by detecting the difference between line of sight and non-line of sight, and then calculating the difference. So it'll ignore the non-line of sight if it can do. And it's using what's called sensor fusion. So it's collecting together all the various sensors in the phone to effectively produce a larger antenna. If you can do that,
presumably, if the UK does commission its own GPS system, then there'd be a tender. So it's not a guarantee that the company that you're talking about would get a slice of the action.
It wouldn't even want to do the satellite system itself. It's to do with what's embedded in the device, in our phones, for instance, or our wearables. The thing about if Britain was going to do it, of course, our technology has moved on a lot in the last 15 years, and the thought is that it would be a low-orbit set of satellites, which obviously spinning around Earth much more quickly, but the amount of power that's generated from the sun could mean that you get more power down on the Earth, and therefore you could get better signals anyway indoors.
So you never know. The EU might come back and say, can we borrow yours?
Exactly. Do a deal.
Peter Cowley, thank you very much. You can catch Peter on his own podcast. That's The Invested Investor. Give him a listen.
And if you'd like to find out more about the news stories we've discussed this week, the links to each of the referenced papers are on our website. That's thenakedscientist.com, along with the transcripts for each interview for every Naked Scientist show ever.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Now, Izzy, why is there a lunchbox with what looks like the remains of your breakfast in the form of a bunch of eggshells, a dragonfly wing perched on the top of it, and a sticking plaster? What's that all about?
I mean, it's not some bizarre diet that I'm giving a go. In fact, this week we're exploring how nature is inspiring the technology and materials of the future. So these are just some examples that we'll be discussing today. Now, this field in general is called biomimetics or biomimicry, but what exactly is it, and how can an egg inspire a new type of building material? I spoke to Michelle Oyen from East Carolina University, formerly from Cambridge University.
Biomimetics is imitating life, and you can take that imitation very literally and try to copy something that's in nature, or you can take it more as being bio-inspired and take ideas from nature and modify them a little bit with engineering principles to try and imitate life in a less literal manner.
We've been doing this for years. Leonardo da Vinci studied birds in the hope of enabling human flight, and he made countless sketches of proposed flying machines. And whilst he didn't quite make it, we got there in the end, but it was in the 1940s, just after World War II, when the field of biomimicry really developed.
There were some very interesting professors who had a broad background in both physics and biology, and he coined the term biomimetic at that time. The field grew slowly from then on into the 1970s, started to grow faster, but it really took off in the 1990s when we started having tools of nanotechnology, because a lot of the structures that we find in nature are nanometer scale. So when we had engineering approaches using nanotechnology, it was much easier for us to imitate nature, and so that's when the field of biomimicry really took off.
Now, we can copy nature in one of two ways.
We can try to literally copy it, so make a direct imitation of something that we find in nature, so like a material like seashell, or we can try and imitate the mechanisms by which that material is made in nature. So we can use our inspiration by thinking about the materials, how they're made, how they're structured, and then maybe not make a copy using the exact same components, but in a similar fashion, so putting the structures together in the same way.
And this is what Michelle specialises in, using natural materials like bone and eggshell to create a new structural material.
These are materials that have good structural properties, good mechanical properties. And of course, they're made under essentially ambient conditions, body temperature being just above room temperature. So both of those materials are composites in that they have multiple components, a mineral or hard component, and a protein or soft component. And so in nature, these materials form by the mineral depositing on the protein component. And so I've been studying how that works and then trying to think about imitating those sorts of materials for use in building structures. So they might be good replacements for materials that we use in the building industry, such as steel and concrete, that are very effective, but that have very, very large carbon footprints, especially as we've been seeing more and more development in some parts of the world, like China. You have contributions to global warming from steel and concrete that's greater than the entire global airline industry. And that's one of those things that would never occur to most people.
In an ideal world, we would mimic nature to create materials that don't require high temperatures to make them, unlike steel and concrete, and therefore releasing less carbon dioxide into the world. But why eggshells and why bone?
Eggshell I became interested in because it has very good toughness, so resistance to fracture. If you think about it, an eggshell is 97-98% ceramic, so it's like your coffee mug, but the 2 to 3% of it that isn't ceramic contributes dramatically to its toughness. And in fact, it's really difficult to crack an egg open. You have to whack it against the table or against the edge of a pan pretty hard in order to open it up. So for a material that's made under chicken temperature, an eggshell forms relatively quickly. So you can go from basically 0 to a solid eggshell in about 18 hours in the course of the chicken's body. And so you have a material that forms very quickly, has very good mechanical properties, and of course hasn't had this energy-intensive process that you would have in normal ceramic or concrete processing.
In addition to creating these artificial structures in ambient temperatures, it's not like we're in short supply of them.
Eggshell is made of calcium carbonate. So calcium and carbonate, carbon and oxygen, these are very abundant elements in the earth, and that's why so much is made out of them. So in fact, eggshell is one calcium carbonate material, but seashells are another calcium carbonate material. Corals, these are all things that other researchers besides myself have been looking at from a biomimicry perspective. Your bones, on the other hand, are calcium phosphate, but again, calcium, phosphorus, oxygen, hydrogen, these are all very abundant elements in nature, and so you don't have to go digging for them or mining for them, they're everywhere.
At the moment, Michelle has been able to grow these artificial structures a few centimetres at a time. So we've got a while to go before we're living in artificial eggshell shacks. But what does the future hold?
The work that I've been doing with biomimicry, with both bone and eggshell thus far, has relied on natural protein, natural collagen. There's a lot of collagen that's essentially left over from the meat industry, and so you can buy it in bulk quantities, but we're using that protein that came from some living cells, living animals. So in fact, the buildings that I would be building from the materials I'm making right now would not be vegetarian. So in fact, one of the things that we're trying to do from a scientific perspective right now is to replace the need for that natural animal-derived collagen with an artificial polymer that we can make in the lab, hopefully something that is still environmentally friendly. And we would have to work directly with the building industry to change the building codes in order to allow these sorts of materials to be adopted in structures where we allow people to go.
That was Michelle Oyen there from East Carolina University. And so that is our eggshell mystery sorted. Onto the dragonfly wing, Chris.
Well, these really are quite something to look at, aren't they, dragonflies? According to the British Dragonfly Society, the maximum speed of a dragonfly is some 10 to 15 metres per second, and in old money, that's 25 to 30 miles an hour. But it's not the speed that we're interested in today, so much as how these insects could help to improve the blades of wind turbines. And Jean-Luc Morissette is from Anglia Ruskin University, where he's studying this. So what's the sort of engineering challenge that you're seeking to surmount then?
So wind turbines don't work particularly well in turbulent conditions. The ones that you will typically see are the ones that look like propellers. The reason why the propeller types don't work particularly well is because they always have to be facing the direction of the wind. So if they're off slightly by, say, 10, 15 degrees, then they stop working. So you have to have costly mechanisms so they can always face the direction of the wind.
I gather that would mean then that you have to spread them out a lot. So obviously they're not very space economic.
Precisely, yes. They have to be spread out quite far from each other so they don't interfere with each other's wakes. We can address this with vertical axis wind turbines, which look like egg beaters.
I'm just picturing that like an egg whisk, a vertically mounted egg whisk spinning round. How does that work then?
With the vertical axis wind turbines, they have omnidirectional operation. Wherever the wind is coming from, they will generate lift. But this also has some inherent problems because on one side, the blades will be facing the wind, and on the other, they will be
They're also
working
facing
against,
the wind, aren't
yes,
they?
they'll be working against it. You have to have higher winds to start the wind turbine rotating. So this is addressed with the Dragonfly design. We see an increase in lift and a decrease in drag, which is what drives the power generation of the turbines.
I was going to ask you, where do the Dragonflies come in then? Now, you've handed me a piece of plastic which has got lots of ridges and furrows in it. Tell me what I'm holding here.
This is based on a cross-section of a Dragonfly wing. And you can see the corrugations there, that it looks counterintuitive if you look at a typical profiled aerofoil that you would see from a plane wing or a propeller. So that looks like a elongated teardrop turned sideways.
With a very smooth surface. So you're saying if we cut a wing across, it would be like a teardrop shape turned on its side.
Yes.
That shape, but it would be smooth, because we're all very familiar with the idea of making smooth surfaces for purposes of being aerodynamic and so on. So why do dragonflies have all these ridges in their wings then?
Okay, it's actually similar to what you see on a golf ball. So the dimples in the golf ball create turbulence, which reduces drag, but also increases lift.
It seems counterintuitive, doesn't it? You make turbulence and that makes you have less drag because the air doesn't stick to the surface as well when it's all turbulent around the ball.
Precisely.
And it would be the same over this wing surface.
Yes, it's exactly the same.
And how does that actually translate into better performance then of that blade if it's got these corrugations?
It increases the lift by causing turbulence and reduces the drag because the passing airflow is not directly interacting with the surface of the blade. Now, with typical wind turbines, you can lose up to 20% efficiency because of soiling of the surface. But if the passing wind isn't interacting with the surface directly, then you won't have that problem. So dirty blades will not negatively affect performance.
Have you built a model then, so you know what if you were to take a wind turbine and design the blades out of a material like this one that you've given me as an example, based on a dragonfly wing? Have you done modelling studies to work out how it would perform and under what sorts of wind conditions, and therefore how much better it would perform if you were to do this?
Yes, so we've run computational fluid dynamics simulations, and they show that we expect around a 26-27% increase in performance.
Straight away? Just by using this shape informed by a dragonfly wing?
Yes, because as well as reducing drag and increasing the lift of the blade, it also delays stall. So once you reach a certain angle, the flow around the wing breaks off and it stops producing lift.
Is it actually feasible to build with this though? Because for the people at home, it looks like, when we're little in the classroom, we used to make a fan by folding bits of paper backwards and forwards on themselves, and you end up with a concertinaed surface. It looks a bit like that, this surface. Could you build something at an industrial scale with that sort of pattern on the blades? Is it feasible?
Yes, absolutely. And it actually should be easier because if you break it down into individual components, they're essentially just a collection of straight lines, and they can be created with recycled materials as well. And because the surface doesn't have to be smooth, because it's not interacting with the passing airflow, then recycled materials have a good place in the manufacture of these blades.
And you're saying that because these vertically mounted turbines would be more immune to the effects of soiled air, kind of lots of turbulence from adjacent turbines, you could pack a lot more of them into less space. So we would therefore our generating capacity for a patch of land would increase.
Precisely. And they would work a lot better in urban environments as well. Typically you don't see wind turbines in urban environments because of the quick direction changes of the wind and the turbulence there. But we see no such problem with these designed.
What about noise? Because people who live near wind farms say that they find, under certain circumstances, the noise quite objectionable. It's a sort of low-pitched, throbbing, whooshing noise that is chronic. It's there all the time, and it really does upset some people. Are these likely to be more or less noisy?
Well, it's interesting that you mentioned that, actually, because research shows that they are less noisy because the surface is interacting less with the air itself. So there's less of a pressure change. So we see a reduction in noise as well.
It's amazing to think that dragonflies, which have been around for millions of years, are now teaching us how to generate electricity better in the 21st century, isn't it? Thank you very much. That's Jean-Luc Morissette. He's from Anglia Ruskin University. Great to have you with us.
Yeah, thank you for having me.
Earlier on, we heard how researchers are using artificial eggshell and artificial bone to develop structure. But once they're made, these sorts of materials can't grow, adapt, or, perish the thought, repair themselves if they get damaged. And this is where our plaster comes in. Future materials will be able to heal themselves. Richard Trusk from Bristol University is developing self-repairing materials, and he began by explaining the struggle confronting a budding biomimicist.
For an engineer or a material scientist as myself, I think that one of the greatest challenges is trying to have synthetic materials that behave in the same way as a biological material. So if you think about nature, we kind of grow materials which adapt to the environment that they find themselves in. We explore different material systems that sort of branch into whether it's a tendon or even your eye. And we're a long way away from being able to achieve that with our synthetic materials. Presently, we would probably take different material systems and bolt them together, which is often very immature in terms of its processing and also sort of not very elegant.
This is a problem that a lot of researchers find themselves in. In nature, whether it's us humans, birds or plants, if we get injured or cut, our clever body is able to heal itself. But technology and engineering don't have this luxury. Well, that's something Richard is hoping to solve.
The research that we've been doing is looking at self-healing materials for aerospace structures. So if you could imagine, you're flying along in an aircraft, something strikes the wing or the fuselage, and initially you wouldn't see the damage, but internally in these sort of advanced materials, there will be a lot of fracture of the matrix material or fracture of the fibers. So the idea for the self-healing network is to be able to restore the performance of the internal structure. We would do this by looking at vascular networks and embedding them within the structure. So a vascular network is something similar to the veins and arteries that you and I have within the human body, and equally the vascular networks that you see within plant-based systems as well, where the sole purpose is to move a fluid to a damage event, to allow the damage event to then be healed, for the structure to be back to 100%. Aircraft as they are designed today aren't necessarily designed for any form of damage. So as we stand here, or we sit here at the moment, then you won't find a vascular healing network system on an aircraft structure. But it is certainly something that all the aircraft manufacturers are looking at, possibly for inclusion in the future.
So that's the scenario if there's an internal break in the aircraft, something that big players like the European Space Agency have looked into. But what if there's a hole that goes all the way through?
There are colleagues of mine over at University of Illinois in America who are looking at how you can get a fluid to sort of bridge a gap. So if we were to punch a hole through a structure, then actually the vascular network could deliver a resin such that it could slowly progress across the surface and then completely fill over the hole to ensure that you had continuity of the material.
Let's take a look at our own vascular system. Thanks to our heart, blood is pumped all around our body, and researchers are exploring a similar system for these aircraft. There would be a central location that would be able to detect when any damage occurs, pump a resin over to that damaged area, which would then fill up a hole or a crack in the system. But one advantage of us over rigid systems is that we can move and adapt.
The way that the sort of materials community is moving now is it's looking at how a material system could react to the environment that it finds itself in, so that it could actually remodel. So at the moment, there's a great interest in the world of 4D printing. So this is taking 3D printing and introducing a smart material that, after it's been printed, can react to an environment to change its shape or to change its properties.
Now, some of us have just about wrapped our heads around 3D printing, the ability to print 3D structures. So what's 4D printing?
4D printing is, in essence, you've taken a smart material. So this smart material could be a shape memory polymer or a shape memory alloy, or even something that's sort of a little bit softer, which is sort of a hydrogel-based system. But the idea is that you would introduce them by using a 3D printer. So there are some changes that you will have to do to the printing process. But once you place these materials into your architecture, you then have the ability afterwards to either use hydration or dehydration or temperature to actually trigger the material to change itself. So the architecture that you print will then change and evolve according to the way these materials change and evolve.
And using this process, you can add or remove water, change the temperature of the material, and with that, it will move or change shape. But why do we need this technology in the first place?
If you think about what we might need for the human body, then we would like some soft structures that could basically go through, say, keyhole surgery and then expand and fill a void or a cavity inside us to sort of repair us. So that in some ways is similar to what you would have with a hip replacement, but at the moment that's done with a very hard metallic structure that's then pushed through and sort of fused into your bone. But 4D materials as a soft construct could actually sort of move in and permeate into the bone structure. Another example would be how it would be used in soft robotics. So again, thinking about how the future of soft robotics, so moving away from these sort of articulated joints, we could use soft materials that could then adapt and remodel themselves depending on where you want them to actually sort of fold and bend. With us in humans, you're looking at specific joints, which is the wrist and the elbow. But in the future, perhaps robotics wants the ability to have a flexible joint. As you can imagine, it could actually be something like an octopus. It has the ability to sort of change where it's folding and where its joints are. So 4D printing would allow you to make a construct where you could actually tailor and design the joint to occur in any location. And then it could actually move or remodel itself to form a joint in a different area. So it could be applied in the field of soft robotics.
That was Richard Trask from Bristol University. And now, Chris, that leads us onto our final topic of crickets.
Yes, indeed. Now, we're all very familiar with these noisy insects, but how can something so small as a cricket make such a racket? And how is this potentially able to inform the technology of tomorrow? Well, with us is Rob Malkin from the Faculty of Engineering at the University of Bristol, who's hopefully going to tell us. Rob, what are you hoping to learn from these insects?
Well, they've been around for 400 million years. They've been evolving. And in that time, they've come up with incredibly elegant, simple and efficient ways of turning sound into some kind of information. We've been at microphones and speaker design for, 150 years. So there's a huge amount of information there that can help us to inspire the next generation of microphone or speaker or even auditory, signal processing and things like that.
Seems funny to think that 21st and 2nd century technology could be informed by something hundreds of millions of years in the making.
Absolutely. And, my background is physics and material science. And when I first became interested in this field and started working with colleagues in the biology department, I was amazed. I'd see really elegant solutions to real engineering problems that maybe the biologists themselves weren't necessarily aware of. It's a goldmine of information, really.
What particular challenge are you hoping to solve?
Personal driver for me is, I have some friends and colleagues who happen to use hearing aids. And if you ever speak to them about what their auditory life is like when they use hearing aids, it's not so great in certain ways, actually. One of the big things is when they're in a room, in a pub or in a restaurant or something, they really struggle to pick out the conversation of the people around them. And the reason is that the microphones are picking up sound from all around, and all that information is really complicated and difficult to understand if you have a hearing aid. So one thing you'd like to be able to do is to take some inspiration from some insects. For example, there's a fly called the ormia. It's a nocturnal fly, and it's able to detect the source of a sound to within 2 degrees. Humans, we can generally do it for around 10 degrees. So these little ears that the ormia has can detect sound really accurately. So it would be amazing if you could have some microphones in the hearing aid that you could switch to like conversation mode. So it will ignore all the sound from everywhere else other than forwards. So the person you're talking to, you'll be able to hear them really clearly, and everything else is essentially muted.
So how does the insect achieve that? Because that really is very impressive, and sound engineers struggle to achieve that sort of performance on a day-to-day basis. So something that's as simple as an insect is doing this with no electricity whatsoever. How?
Well, this is a really amazing thing. Only recently have we come up with the technology to be able to actually understand what it is that the insects themselves are doing. How is the ear moving? What's the ear made of? It's just one thing knowing what the ingredients are that go into making an insect ear. But when we use electron microscopes and things like this, we're finding that the ear isn't really a material. The ear is a structure. These ears are so thin that it's 600 nanometers thick. Much, thickness of a human hair, that kind of size. But within that thickness is different materials laid down in different orientations. So really, it's not a material; it's a structure. And those ears, they've integrated the three processes which we use to hear. So we tend to hear in three stages. We hear the sound collected by our outer ear, we amplify it in the middle ear, and then we process it in our cochlea, and then that signal gets into the brain. The insects do that, all three of those things, on the ear itself. They collect it, they amplify it, and they process it on the ear, all mechanically. No electricity, nothing. So that's really the key, is to try and understand the physics of it a little bit better, and we're trying to see that in exactly how we're going to improve the next generation of hearing aids and any microphone really, or speaker themselves.
So could you take what the insects do and then effectively 3D print a miniature artificial version that basically works the same way, except will interface with the electronics in a hearing aid, so that user can focus the direction of pickup on what they're looking at, so they get rid of all these distracting sounds?
Excellent question, and essentially the answer is not yet. You've got two types of making something. One is you remove material, like you start with a block of metal and remove it mechanically, or you start at the bottom with very low-scale nano printing, 3D printing techniques. And the insects and all these structures are just about in the middle there. And really, we're not quite there in terms of engineering. We know how these insects work and how their ears work, but I think the technology to replicate them could be, maybe a good 10, 20 years off.
Even so, it's amazing to think that we're beginning to make progress in that direction. Rob, thanks very much for joining us to talk about it, and we wish you luck with your cricket-inspired hearing aids in the future. That was Rob Malkin. He's from the University of Bristol. So who knows, you might even be listening to this programme on a cricket-inspired microphone in the future. Thank you to our other guests this week as well. Jean-Luc Morissette, Michelle Oyen, Richard Trask, Peter Cowley and Chris Proctor.
And we've just got time for Question of the Week. And this week we've been sniffing out an answer for Twitter user Andrew.
Hi guys. Do wild animals also suffer from allergies? And if so, does this occur at the same rate as in humans?
Allergies are no fun, but do wild animals suffer as much as we do? On the forum, one user, Dead Cat, says, why wouldn't they? Humans and other domesticated mammals are all animals. To help us answer this question, we turn to Andy Flies, a wild immunologist from the University of Tasmania.
The short answer is yes. Animals do get allergies, but not at the same rate as humans. However, the distinction of wild animals and not just animals makes the question much more interesting to this wild immunologist. The number of documented cases of allergies in wild animals is tiny compared to the number of allergy cases in humans and domestic animals. This could be a sampling bias because domestic animals are regularly observed by their owners, and thus allergies are more likely to get noticed and reported than for an elusive wildcat.
I think the sheer number of pet sneezing videos on the internet probably backs that up a little.
Alternatively, natural selection could make it difficult for animals with allergies to survive and reproduce. For example, think of a leopard stalking its prey, only to sneeze when it gets close. From a scientific point of view, the higher rate of allergies in captive animals than in wild animals is a fascinating parallel to the rise of allergies in industrialized human society. There are many hypotheses as to why there has been an increase in allergies in humans in the past century, but most of them revolve around humans being disconnected from the environment in which we evolved. As human society has urbanized, we have become less likely to be infected with the microbes and parasites with which we co-evolved. The immune system needs to be trained by early and continuous exposure to microbes and parasites for proper development. And without this training, the immune system can end up attacking the wrong targets, like harmless pollen. Giving your dog bottled water might send it down the same allergy-prone path that many humans have trodden.
Thank you, Andy, for helping sniff out an answer to that question. Next week, we're leaving allergies and the whole planet behind as we go to the moon to answer this question from Chad.
Is it possible to terraform the moon so humans could live there long term.
It sounds like sheer lunacy to me. Do you see what I did there? Anyway, have you got an answer for us? Or have you got a question that could become next week's question of the week? In either case, write to chris@thenakedscientist.com. You can also tweet @nakedscientist. We'll pick them up there. Or you can go on our Facebook page. It's facebook.com/thenakedscientist. There's also a forum on our website, nakedscientist.com/forum, where there is a board specifically for question of the week. And the new question and last week's answer I'll put there for you to read up on. Now that's it for this week. Thank you very much for joining us, and do be sure to tune in next time because we're going to get quizzical with a Q&A programme. So if you have any questions for our panel of experts, send them in through all the usual channels, including the ones I just said, and we'll attempt to get them in to this or one of our future Q&A shows. The Naked Scientist comes to you from Cambridge University and is supported by the EPSRC and Rolls-Royce. I'm Chris Smith, and thank you very much for listening. Goodbye.